So now we're going to move from our conversation about polynomial functions into a conversation about rational functions, and then we're going to tie them both together in 4.6 with polynomial and rational inequalities. So what is a rational function? Well, a rational function is anything that has an x in the denominator. So it says here a function formed by the quotient of two polynomials, but specifically we're going to have this polynomial in the denominator. And anytime you put an x in a denominator, you have to be really careful that that value of x doesn't make the denominator equal to the zero. So whenever we're talking about a rational function, we have to talk about their domain. The domain is the possible values for x, and we're going to exclude things that would make the denominator equal to zero. And now what we're going to do, because that's something we already know and we've solved rational equations, but now we're going to talk about what that does to a graph. When we have those domain restrictions where x cannot equal something for a rational function, we're going to get what we call vertical asymptotes, and your graph is going to exhibit asymptotic behavior. So a vertical asymptote is an invisible line that your function will approach but not cross. So let's look at a function like y equals x minus, or y equals 1 over x minus 3. Now I've got this really nice chart here, but I find sometimes seeing it live in Desmos could be helpful. So one sec. All right, so I just quickly threw up my graph. So this is y equals 1 over x minus 3, and I'm going to drag my mouse on this graph, and we're going to approach this x value of 3. And sometimes it's actually nice to draw that invisible vertical line at x is equal to 3. So here's my asymptote. So this is my invisible line that my graph is approaching but never reaching. Now let's approach this asymptote on my graph. So let's start in here. Let's just start looking at 2. So somewhere at -2. So this is an x value of 2. I have a y value of -1. As I go along, my y values are getting bigger and bigger and bigger as my x value gets closer and closer to 3. And now actually I'm going to zoom out a little bit so I can just scroll down a bit more. Okay, so let's keep going. So let's go down to an x value of 2.95. We're at -22. Let's go down to x equals 2.9611. We're at y equals -25. Let's scroll out more. In fact, if you scroll out more, you can't really see it, right? But let's drag, whoop, I'm the wrong guy. I want the blue graph. There we go. If I drag along this blue graph, I'm going to go way down here, if it'll let me. Right? So I'm going to drag down. What's happening is this blue graph, the y values just keep going negative and negative and negative. In fact, my y values are approaching negative infinity. So looking here, right? So when we increase those x values, my y values are getting bigger and bigger. It wasn't letting me drag past 2.96 apparently. So let's say it was 2.99. You got a y value of -100. Then you go to -1,000, 10,000, 100,000. So as my x value is approaching 3 from the left, my y value was approaching negative infinity. When we look at our graph approaching 3 from the right, let's just look here. So as I come in from the right, what's happening to my y values? Well, they're going up and up and up, and in fact they keep going up. So the y values, as my x values approach 3 from the right, my y values are approaching positive infinity. This is asymptotic behavior. So anytime you have a value that x cannot equal, there's this imaginary vertical line, and then your graph will either approach a positive infinity or negative infinity. So let's look at 3 different examples of pictures. This first one I have y is equal to 1 over x. This is kind of like your classic or your base rational function. This would have a domain that x cannot equal 0 because you have just an x in the denominator. And your vertical asymptote is whatever that domain can't equal. So if you have a domain of x cannot equal 0, your vertical asymptote is x equals 0. What about if we have an x squared in the bottom? Well, the domain is x still cannot equal 0, and my vertical asymptote is still x equals 0, but look at the difference in the behavior. With this graph, from the left I'm approaching negative infinity, from the right I'm approaching positive infinity. For this one, from the left I'm approaching positive infinity, and from the right I'm approaching positive infinity. This is not usual. Usually they do this alternating thing where you kind of approach from either side, but because the denominator is squared, my graph can't be negative. So I get this approaching infinity on both sides. Here's another example. So for this one, again, my denominator is x cannot equal, x plus 2 cannot equal 0 when x is negative 2. X minus 1 cannot equal 0, so x cannot equal 1, which means my vertical asymptotes are negative 2 and 1. And if you look at your asymptotic behavior, I could add in those asymptotes. So there's an asymptote at negative 2, there's an asymptote at positive 1. I'm approaching negative infinity, and positive infinity again. And then on the right-hand side, I'm approaching negative infinity. And then this last one, I did make a couple changes in these notes last minute, so if you have an old version of the notes, I apologize. Just kind of absorb this in. Your picture might be a bit different. But for this one, when you look at my denominator, so again, it didn't matter about the numerator. The numerator does not determine your domain. For this one, x cannot equal 3 and negative 1, so negative 1 and 3. And for this one again, my asymptotes are negative 1 and 3. This one, when you look at the asymptotic behavior, it's a little bit different, which is why I chose this one instead of the one that was originally in the notes. If you look at this one, we're approaching negative infinity, and then there's this like swoop in the middle. So we've got this up to down, so we're approaching positive infinity, we're approaching negative infinity. And then on the right-hand side, we're approaching positive infinity again. So I wanted to give 4 representations of sort of the different shapes or different asymptotic behavior that rational functions can have. So there's this like classic kind of corner behavior. Then there's a U that can come, and then there's also this kind of crossing the x-axis that can happen between two vertical asymptotes. Before we finish the conversation on vertical asymptotes, I have to tell you one exception, which is that sometimes a domain restriction is not necessarily a vertical asymptote. Sometimes it's what we call a hole. It's not a what we call, it's just a hole. And this is going to happen in one very specific circumstance. If, when you factor your numerator and your denominator, there is a common factor between the numerator and the denominator, then you're going to get a hole where that happened. So for example, if I take this function, x squared minus 4x, so this polynomial, and I factor it, I have x times x minus 4. If I do the same thing with the denominator, I factor out an x to get x times x squared minus 1, leaves me with the difference of squares, so it would be x minus 1, x plus 1. If I asked you what is the domain of this rational functions, you'd look at the denominator and you'd say x cannot equal what? Well, 0, 1, and negative 1. I know those aren't in order. If you want to put them in order, it's actually driving me nuts. I'm going to put them in order. So x cannot equal negative 1, 0, and 1. But if you look really closely at this function, you'll notice that in the numerator and the denominator, there's this common factor of x, which I could simplify and get a new function of x minus 4 times x, or divided by x minus 1, x plus 1. And in fact, this is the function that we would graph. This is what we would use to graph the function. And from there, I'd say, okay, the asymptotes are 1 and negative 1. Those are going to be the vertical lines that you approach but can't touch. But then there's going to be a hole. Because this is the function that we're graphing, there is this common factor of x in it. I cannot put in x is equal to 0, or it makes my denominator of my original function 0, which is undefined. So I have to do something about that. So this 0 is a domain restriction. So I was trying to figure out how to change color. This 0 is a domain restriction, but it's also going to be where my hole is at x equals 0. Now, you want to go further and find what the y value would be. To find the y value of the hole, you're going to plug in x is 0, not into the original function, because that'll give you undefined, but into this simplified function that you would graph. So we get 0 minus 4 over 0 minus 1 times 0 plus 1, which would give you negative 4 over negative 1, which is positive 4. And we'd have a hole at 0, 4. So again, this is an exception to the rule. So the majority of the questions that you are going to sketch are going to be like this, where there's no holes, right? There's no common factors. But if you get one with a common factor, take the common factor away to sketch, but that common factor did exist, and so it produces a hole in your function. Let me just prove this to you by graphing it in Desmos. Okay, so instead of you having to watch me go back and forth to write this in, I just did it. So this is my graph. Y equals x squared minus 4x all over x squared minus x. Now we said there was a vertical asymptote at x equals -1. Oh, there it is. Good, I have that asymptotic behavior. We have another vertical asymptote at x equals 1. But then we said there was something that was going to happen at x equals 0. And if I draw an asymptote, it doesn't work. The asymptote crosses your graph. But what we want to look at is where does that asymptote cross that graph? So we're going to look right here when x is 0. So I'm going to get rid of the asymptote. Then I'm going to focus in on the graph itself. And I'm going to try to hit it perfectly. We'll see. Close. Let's get 0. There we go. When x is 0, the y value is undefined. Because if I put 0 into the original function, you can see that it would make the denominator equal to 0, and my graph is undefined. Now, no matter how much I scroll in, the graph never puts an open circle, but when I hover over it, you can see that an open circle came up. If I pick any other point on the graph, it's a closed circle. Okay, so to see these holes in Desmos, you actually have to physically touch it to make it happen. I'm never going to be able to touch it again. Anyway, you saw it. And then the other thing I wanted to prove to you is just that when we take that common factor out, what we are going to actually graph is what's left over. So the x minus 4 in the numerator, and then the x minus 1, x plus 1 in the denominator. And I just want to show you that even though I've put on this new graph, and I could actually make it a different color so you can see that there's a difference. Okay, so if you look at this, this is the red graph. This is the blue graph, red graph, blue graph. They're the exact same. So when we're graphing a function, you always want to graph your original function, but you're allowed to graph the simplified version of it. You just have to make sure all the domains stick. Okay, so last thing for this note, we're just going to go back in here, or this video, is we're just going to practice these top 2 questions. I've factored them for you, so that's already been done for you, and we are going to determine the domain of these functions, any vertical asymptotes, and then the locations of any holes if they exist. So for this first one, let's talk about domain first. You just look at the denominator, and the denominator cannot equal 0. So x cannot equal 0, 3 halves, and -1. So -1, 0, and 3 halves. Now out of those, which of them are vertical asymptotes? Well, maybe we should simplify the function first. If I simplify out that common factor of x, I'm left with an x squared in my numerator, and then I have a 2x minus 3 and an x plus 1 in my denominator. The x went away. So my vertical asymptote won't include the 0. It'll just be -1 and 3 halves. Then to find the hole, we're going to have a hole when x is equal to 0. To find the y value of the hole, we're going to plug 0 into here. So we're going to find the value of h at 0. None of that looks right. H at 0. And I'm going to go 0 squared, so into your simplified function. 2 times 0 minus 3 times 0 plus 1 is going to give me 0 over, who cares, -3 times 1, -3. I get 0. So this graph would have a hole at 0, 0. And again, if you want to check it, you're going to plug this into Desmos, and then you are going to scroll in, and you'll notice that there is a hole when x is equal to 0. All right, what about this one? So for this one, again, we've got domain. We're going to look at my denominator. Denominator cannot equal 0, so we've got 0, positive root 5, and negative root 5. So I'm going to write those in numerical order. Negative root 5, 0, and root 5. Then we want to check to see if there's any common factors. Well, it's an x minus 2 in the top, so I can't have a common factor, so this time all of them are going to be vertical asymptotes. We would have x equals negative root 5, 0, and root 5. And again, if you want to check, feel free to plug these into Desmos, but just know domain is at the original function. Nothing can equal 0. Then the vertical asymptote is after simplification. Anything left, those are the equations of the vertical asymptotes, and then the things that went away, those x values will make holes. Find the y value by plugging in value for x into your simplified function. All right, good luck on that.